Hello class, welcome to lesson 6.4. So we're going to be proving that quadrilaterals are parallelograms in this lesson. So which properties determine whether a quadrilateral is a parallelogram? We want to be able to use properties of sides, angles, and diagonals to identify parallelograms. So let's start with a theorem of a parallelogram. First off, a parallelogram is called such because you have two pairs of opposite sides that are parallel, and hence why it's called a parallelogram. Now here's the first theorem. This is actually a converse of a theorem we discussed in another lesson, the converse of theorem 6.7, which stated that if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. So if you have a parallelogram and you know that this side is 5, then the opposite side is also 5. If this were 3, then the opposite side would also be a length of 3. Now, the theorem 6.7 stated that if you had a parallelogram, that this was the case. Now, for the converse, we're stating that if the sides have this property, then that means that the sides themselves are parallel, and therefore we have a parallelogram. So this is the reverse of what we had in that other theorem. So we're gonna actually prove this theorem. So this lesson is going to be very proof heavy. We're going to have some examples, but by and large, a lot of examples will be proofs of the theorems, since this is a specifically proving lesson where we're proving quadrilaterals or parallelograms. So we have a supposed parallelogram. We want to determine if it actually is a parallelogram, and we know that it is from the theorem. So we want to basically prove that theorem. So we're given that AB is congruent to CD, and AD is congruent to BC based off of the tick marks here that you can see. And what we're going to do is we're going to construct a diagonal to help us with this proof. So we know that this diagonal BD is congruent to itself by the reflexive property. So we can essentially put a separate tick mark there and say that it's congruent to itself. And this is because when we draw this diagonal, we end up with two triangles, and we want to show that these two triangles are congruent. So because we have three sides, we have a side, 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 and a side, side, side here for these two triangles. This means that by SSS, these two triangles are actually congruent. And this is exactly why we drew this diagonal. So now we know that these two triangles that we divided this parallelogram into are congruent. So because of that, we can state that by the CP/CTC, the corresponding parts of congruent triangles are congruent property here, the theorem. We can state that this angle right here, which is ABD, or rather this angle right here, which is ABD, is congruent to this angle, which is CDB. And this is purely because of CP/CTC. Remember that CP/CTC stated that if you have two triangles that are congruent, that means corresponding angles are also congruent, and so on. Okay, so now that we know that these are congruent, this actually proves that these lines are parallel. And that's because of the converse of the alternate anterior angles theorem. So because of that, we can directly say that BC is parallel to AD in this case. Because remember that these are alternate anterior angles here. Okay, and similarly, we can similarly state that so we know if we kind of draw this out, we have this parallel line, and this transversal. You can see that those are alternate anterior angles. Now, if we draw the other parallel lines, so let's say we focus on these lines here, these sides, and we drew a transversal, notice that those are also alternate anterior angles. And so no matter which way you draw it, these two lines have to be parallel. So therefore, for this final shape, we can go ahead and say that this is parallel and this is parallel, and therefore this is a parallelogram by definition. Okay, so we went ahead and proved that theorem. We're going to look at another theorem of parallelograms. And this one is the converse of theorem 6.8, which was also a lesson that a theorem that we talked about in lesson 6.3, which stated that the theorem in 6.3 stated that if you have consecutive interior angles, which are angles that are next to each other back to back, then they're supplementary. Now, this theorem states that if you have supplementary angles that are consecutive, then you have a parallelogram. Okay, so B and C are consecutive, so are A and D, for instance, and so are A and B, and so on. So that was converse of theorem 6.8. The converse of theorem 6.9 stated that if you're looking at opposite angles, for example, B and D, they're usually congruent in a parallelogram. So if you know that they're congruent, then that means you're looking at a parallelogram. So we're going to prove the converse of theorem 6.8 first. So we're going to prove it with this example. So looking at this example, they state that F and G add up to 180, and F and J add up to 180. So let's prove that it's a parallelogram. So first, we know that F and G are supplementary because by definition, if they add up to 180, then they're supplementary. And because they're supplementary, so these ones right here, those two angles, this means that they're same side interior angles. And that's because if you were to draw this out like this, or rather if you were to draw this out like this, then you would, and then with a transversal, then you can see they're on the same side of the transversal, and they're also interior angles. And so they're same side interior angles. And therefore, by the converse of the theorem, the postulate, these must, or not that one, but these ones must be parallel, those sides. So now we know those are parallel, and I'll leave that on the diagram. And here's just a drawing of that. What I just drew earlier. Now, since F and J are supplementary by definition here, similarly, we know that they're same side interior angles. And the way you can think about it is you have F and J right here. And if you were to look at these two sides and this as your transversal, which I'll actually show you in this next here, the blue lines and the red transversal, they're same side interior angles, similarly to what we said earlier. And therefore, those blue lines are parallel. All right, so then by definition, because we have two pairs of opposite parallel sides, we have a parallelogram. End of proof. Okay, so now let's prove the other theorem, the converse of theorem, I believe it was 6.8. So we want to prove that, well, if we know that the opposite angles are congruent, so we know that these are congruent, then we have a parallelogram on our hands. Okay, well, since we know that the polygon is a quadrilateral because it is a parallelogram, then that means that the interior angles have to add up to 360 because of the polygon interior angle sum theorem. Remember, the polygon interior angle sum theorem stated that if you had a polygon with n number of sides, then the sum of the interior angles is given by this formula right here. And so for a quadrilateral with 4 sides, it was simply 4 minus 2 times 180, and then 2 times 180 is 360. Okay, so therefore the angles add up to 360 here. Now we do know that n is congruent to L, and therefore in this formula we can replace n with L. So we can replace this with L, angle L, and similarly we can replace O with M in this equation, and so we get this. And then we can go ahead and combine these. So you have 2 of these and 2 of the m's, and therefore we say we have 2 of them in total is equal to 360. Then we can divide off the 2 on both sides by the division property, and we get that L and M together equal 180. Similarly, well, because we know that they add up to 180, that means they have to be same side interior angles. And because they're same side interior angles, that means that these sides have to be parallel, similar to what I did in the other example. Okay, so now let's repeat this process. Instead, now we're replacing n for L. So n is gonna so we're gonna do the opposite of what we did. Instead of replacing this, we'll replace the other one. And if we do that, then we get that n and O add up to 180. And so we know that n and O add up to 180, and therefore they're same side interior, and therefore these are parallel. Okay, and that was the same that we did earlier. And so by definition, that means that element O has to be a parallelogram. End of proof. All right, so let's look at some examples rather than just a proof of the theorems. So we were able to prove those three theorems. Let's apply them. So is DEFG a parallelogram? Explain. So we have opposite angles are congruent. And we know that these are consecutive interior angles. They're next to each other. And notice that they add up to 180. Now, because they add up to 180, that's a good thing. And because you have opposite angles are congruent, well, then that means that if this is 27, this is 27. And that is true because if you were to add all these angles, you're going to get 360 in total. So this is definitely true. This is a parallelogram, and we can say that this is using the converse of that one theorem that we proved. I believe it was converse of theorem 6.8. So you got opposite sides are congruent, and therefore we have a parallelogram. Okay, so this is definitely a yes. And explaining it, you can just cite the proof that or the theorem that we used in the other slide. For part B, is elemento a parallelogram? Explain. So if you look at the opposite angles here, the angles are not congruent, which they should be congruent for a parallelogram. Also, notice that these two angles do not add up to 180. So 91 plus 91 does not equal to 180, and therefore we can't really use the converse of theorem. I believe it was theorem 6.8, and therefore this is not a parallelogram. Okay, so let's look at another example. For what value of the variable is the quadrilateral a parallelogram? So if we use the theorem that we talked about in the beginning, I believe it was converse of theorem 6.7, if I'm not mistaken. But I don't memorize the numbers for the theorems here, but it was given in the first theorem in this lesson. But we know that for a parallelogram, these two sides have to be congruent, and then these two sides have to be congruent. And if that's true, we have a parallelogram. So we have s plus 5 is equal to 2s minus 2. We can set those sides equal and solve. And then similarly for the r, we can set that equal to each other and solve for r. So we'll solve for s first. Let's go ahead and subtract s here. So we get 5 equals s minus 2. And because we have s minus 2 equals 5, that means s has to be 7. Okay, and then looking at the next one, we're going to subtract 4r on both sides. So 7 equals 3r plus 1. We'll go ahead and take away 1 now. We get 3r equals 6, so that stands to reason. R equals 2, because 3 times 2 is 6, right here. Okay, let's look at the part B. We know that opposite angles are congruent, and then these opposite angles are congruent as well. So we're going to set them equal to each other for a parallelogram. So 5a equals 3a plus 14. All right, we'll subtract 3a on both sides, leaving us with 2a equals 14, which means that a has to be 7. 7 times 2 is 14. And then we'll set these angles equal. 4b plus 1 is equal to 3b plus 37. We'll subtract 3b on both sides, leaving us with b plus 1 equals 37, which means B has to be 36 because 36 plus 1 is 37. All right, so let's talk about converse of theorem 610 and 615. So the first theorem, this converse here, the original theorem stated that if you have a parallelogram, then the diagonals of that parallelogram bisect each other. They cut each other in half. This theorem states the reverse, that if the diagonals are cut each other in half, then you have a parallelogram. Okay, so notice that the diagonals are not the same length, but they do cut each other in half. For the theorem on the bottom, which is the converse of theorem 615, the original theorem stated that if you had a pair of opposite sides and they were parallel, then you had a parallelogram. This is doing the opposite. So if you had a parallelogram, then you would have two sides that are the same, that are opposite, and parallel. Now this is stating the reverse of that. So let's go ahead and prove the converse of theorem 610 first, which stated that if these diagonals bisect each other, that we have a parallelogram. So let's begin that proof. So we're going to do a two-column chart here. We know that the what's given are that the diagonals bisect each other. The second statement that we're going to use is the fact that in this case, AXD right here is congruent to BXC or CXB right here because of vertical angles. Similarly, and I'll redraw this just to make this more clear. So these are congruent. This angle is congruent to this angle by vertical, and these are congruent on the opposite side because of vertical. Okay, so now by S side angle side and side angle side, we can conclude that the triangles are congruent. Same thing here, side angle side, side angle side. So we can prove that all of these triangles are congruent. So, or rather that these two pairs of triangle and these two pairs of triangles are congruent. Okay, so now that we know that these triangles are congruent, now I'm just going to focus on that. So these are congruent. Then by the CP/CTC, we know that this has to be congruent to this because those two triangles are congruent to each other. So that stands to reason that those sides have to be congruent. And these two triangles, 1 and 2, are congruent. And that stands to reason that this is also congruent to this. Okay, so now that we know that the triangles are all congruent and they're actually, they're congruent to each other rather, and these are not the same measure here. These could be different measures. So I'm going to use 4 tick marks to distinguish this from this. So these are the same, and then these are the same. So therefore we have a parallelogram with two opposite sides that are parallel, or that are congruent, and that's the converse of 6-7. And we proved this theorem already, so we can use this theorem for this proof. Let's prove the other theorem. I believe it was converse of theorem 615, which stated that if you have two sides that are opposite, that are congruent and parallel, then you have a parallelogram. So what we're going to do is we're going to construct this diagonal. We already see it on the diagram here in order to help us with the proof with the triangles. So we know that KL is parallel to JM. And the diagonal here serves as a transversal. So we can think of this as two parallel lines with a transversal like this. And therefore we can state that KLJ, this angle right here, is congruent to this angle right here because of alternate interior angles. This is a theorem in chapter 2. So we can state that those two angles are congruent, and I'll draw this more clearly on the diagram. So those are the same. Now, because we're given that, so because we have this is the same as this, and we know that this side is congruent to itself, so I'm going to put this as a double tick mark. That means that these two triangles, that one and this one, have to be congruent. They have to be congruent by side, angle, side. Side, angle, side. So they're congruent by SAS. So now that we know that those triangles are congruent, we can go ahead and state that JK is congruent to LM because those two triangles are congruent and therefore the sides have to be congruent. And since we have two opposite sides that are congruent by the converse of theorem 6-7, we know that we have a parallelogram. End of proof. Okay, so yeah, that was a lot of proofs, but we should be done for the proofs. So let's go ahead and apply the theorems that we proved here. Are the following quadrilaterals parallelograms? Explain. So we know that these two angles are consecutive interior angles, and notice that they add up to 180, so that's good. Because they add up to 180, that means that they're same side interior angles. Let me explain that. So that means that you can think of these as parallel lines, and this is my transversal, and these are same side interior angles from chapter 2. And we know that same side interior angles from that theorem add up to 180. And therefore that proves that these two lines are parallel. And then using the converse of one of the theorems that we had earlier, where if you had two sides that are the same and that are parallel, we can use that theorem to prove that this is a parallelogram. So yes. And I believe this was a converse of, trying to remember, it might have been converse of theorem 615 that stated that if you had this condition, you have a parallelogram. Now for part B, you only know that the diagonal bisects here, but you don't know that this is true. You don't know that that's true. So they don't tell you that in the problem. So because they don't tell you that the diagonals bisect each other, and they don't tell you anything else on this diagram, we cannot conclude that this is a parallelogram. If we were somehow able to conclude that that's true, that those are the same, then we can conclude using a converse of one of the theorems that this is a parallelogram. But unfortunately, we cannot. So there's not enough information to be able to determine this. All right, guys, that's going to do it for the lesson. I hope you took something from this. I hope you learned something. And as usual, I'll see you in the next one.